Good morning, everyone. Thank you for joining this webinar. Thank you, Mary, for introduction and for inviting me to share my research on and share the all about the Raman spectroscopy and how it can help close the loop in circular economy. So I come from the laser lab, Coimbra Laser Lab, which is located, which also is part of a Coimbra Chemistry Center, which is located in the beautiful city of Coimbra at the University of Coimbra. This is our department. This is a closer photo. So let's start. This is the outline of my talk. So first I'll give you a little bit of theory, fundamentals of Raman spectroscopy. Then we also touch on instrumental aspects of Raman spectroscopy, on its advantages and limitations. And then I give you a few example studies, practical applications of Raman spectroscopy. And then hopefully by the end of the talk, we will be able to answer the question if the Raman spectroscopy can be useful for research in the field of circular economy. So let's begin. So what is Raman spectroscopy? So Raman spectroscopy is based on Raman scattering, which is inelastic scattering, meaning that the energy of the light, which we shine on our sample, will change due to the vibrational modes of our molecule. And this way we will get information about the structural composition of our sample. So let's look at this diagram, which will help us understand a bit better. So there are three processes, or let's say rather four, could happen when we irradiate our sample with, in this case, monochromatic collimated light as a laser light. First, we will be observing a relay scattering, which means that our system will go to some virtual state and then return to the same ground vibrational state without change of energy. This scattered light does not bring any information about vibrational structure of the sample. And then the other process, which is much more weaker, approximately one photon in a million, will have a little bit different energy from the energy of the laser, and the energy difference will correspond to the excited vibrational state of our system. And then another process, which is even less likely, is the anti-Stokes scattering. So Stokes scattering is usually what is presented and the mostly used, but there is also even less probable process, which is called anti-Stokes scattering, is when our system gains energy after the scattering, when the energy of the scattered light is a bit larger than the initial energy, and this happens because the system returns to the ground vibrational state from the excited vibrational state, and this energy difference again will correspond to this vibrational level. And another process here, which is marked here on the diagram, is the fluorescence, which is unfortunately for this case of Raman spectroscopy is not desirable because it's much more efficient and it gives a huge background which will hide actually the Raman signals. We will touch on this a bit later. And here also on this diagram, we'll see the comparison with the infrared spectroscopy, infrared absorption, where we have a broadband source of light, and we directly monitor which light is absorbed by the sample. So these two techniques, Raman spectroscopy and infrared absorption, are complementary, and they give complementary information because not all vibrations will be active in Raman and vice versa. So usually they complement each other. So, okay, let's now discuss the instrumental aspects. This is actually the spectrometer that we use in our lab. It's by Hariba, Labram Evolution Raman microscope. So this is a typical schematic of a confocal Raman spectrometer, or I would even say Raman microscope, because there are two important parts, two improvements. So we are using a microscopic objective, so we can focus on a study our sample in great detail and focus on small areas. This is the sample table. And then also we have here a confocal hole, which I will show you in a minute. So let's focus first on this part of the Raman spectroscopy. So this confocality, as I said, is an important improvement, and it gives us the ability to have high spatial combined with the microscope objective to study the sample with high spatial resolution. And the construction of the microscope or this is so that the confocal hole just blocks, as you can see in the schematics, the light which comes from out of focus of the objective. And this way we can have a 3D resolution. We can study the sample with in 3D. And the size of the hole will govern how much area we are studying by. The wider the hole, the larger the area will be studied by our system. And then, of course, it also depends on the objective. We can have a long distance objective, or with small magnification, then we will have a larger area, larger volume will be studied. But a bit less Raman light will be recorded due to the typically lower numerical aperture of such objectives. Or we can have a high magnification objective, which is typically used, like 100x objectives, which will give us higher spatial resolution. We will collect from a smaller area, but we collect larger. We will have a larger angle of collection, so larger amount of Raman light will be collected in this way. Okay, now let's take a look at the spectrometer part. So after the confocal hole, or rather, let me explain from the beginning. So when we have the laser, usually the laser is a visible laser, or could be near infrared or UV laser. The radiation first comes to the edge filter. This is also an important element, and there are two functions of this element. First, it will guide the light to the sample through the objective, and then when the Raman light is collected through the same way, it will let energies, in this case smaller than the laser energy of the laser, pass to the spectrometer through the confocal hole. But our light is still not spatially resolved, so it's on the same path. We need to somehow spatially resolve the light before we put it on the detector. So this is the function of the spectrometer. Here's the light comes to the spectrometer and then passes. Then it's the main optical element here is the grating, which is spatially distributes the light based on the frequency. So it can be focused on the detector in different points, different pixels of the detector. And here is the important aspect is the focal length. So focal length is basically the distance the light travels inside the spectrometer, and the larger the distance, as we can see here, the higher the resolution we will have, because less spectral region is focused on the same detector. So we have a short focal distance. All the light will be caught by the detector, and then we will have a larger spectral region, but the bands will be less resolved. Or if we have longer focal lengths, then we will have a higher spectral resolution. And of course, this requires a bit larger spectrometer. So in this case, the larger, the better. So let's come back to this fluorescence issue that I mentioned. So it can actually, as I said, can sometimes, for some samples, fluorescent samples, it can hide the Raman signal. It's because since we are using the visible light, laser light, it will also, of course, for fluorescent samples excited. And what happens is it can, as I said, it can block completely the Raman signal. So here we can see we're exciting at 532 nanometers, somewhere here. So basically, this is a spectrum of some polymer. And we see that there is a very broad broad, strong signal which comes from the fluorescence, and there are some narrow bands which are actually this the Raman signal which we are interested in. But then if we switch to another laser, so remember the diagram, it doesn't matter which laser we use because we are exciting our molecule to a virtual state, and it will come to an excited vibrational state, same vibrational state. So what matters is the energy difference. But we are working now in a different spectral region, and we see now a bit less fluorescence because now we're exciting with 633, which is a bit, the photons have less energy. And now we can see the Raman bands a bit better. And then further, the situation improves even better if we use a near-infrared laser, and then we are in the tail of the fluorescence, which is now becoming quite low, and then all the Raman bands are much more visible. So this was the absolute scale in wave numbers and wavelengths. But now we have to switch to wave numbers, which is how usually the Raman spectrum is presented. So here we have the Raman shift, which is a difference between the energy of the Raman light and the relative to the laser light, and then in reciprocal centimeters. So this is the first spectrum which was recorded with the green laser. Now the red laser improves the situation, so we can see now they are at the same region. And then and this is our best spectrum, which is already acceptable. We can easily correct this baseline and then have a Raman spectrum of the polymer. So here also, besides the advantage of reducing fluorescence by using near-infrared light, there is also another effect, optical effect, which is when we use a longer wavelengths of the laser, we will have a higher spectral resolution. And this happens because the optical element, the grating will reflect the light at higher angles due to the higher wavelengths, which we are not working. And this diagram shows that with the green laser we are covering the whole region, and then with the red laser we cannot capture the whole spectrum, the same Raman shift. With just one position of the grating, we have to move the grating twice because here you see the length of the CCD chip does not change. And then finally, for the infrared laser, we have to change the position of the grating 3 times to cover the whole spectral region, which is now just still the same, but now it corresponds to 252 nanometers. And that, of course, increases the time of collection. But then at least we are gaining the highest spectral resolution of the spectrum in this case. Okay, before we continue to the practical examples, let's highlight some advantages and limitations of this Raman spectroscopy. So, of course, first main advantage, this is a non-destructive technique suitable for precious and irreplaceable samples, for example. Of course, this has to be, we have to take into account that we are using, in the case of the Raman microscope, we are working with laser light focused into very small spots, about 1 micron. So in principle, we can damage the sample by the power. So we have to keep the power down, and then the technique will be non-destructive. So there is no sample preparation usually involved. We can study a wide range of application of samples. It could be solids, liquids, gases, and then different types of fields, material science, chemistry, biology, and so on. We get detailed information about the structure of our system by analyzing these vibrational modes. We can use this technique for both qualitative and quantitative analysis. Qualitative is easier, but quantitative is a bit tricky because there are several parameters which can affect the intensity of the bands. It's possible to do. We can do also in situ in real-time measurements. Another important advantage is that it's not affected by water interference. We can study water solutions, unlike infrared spectroscopy. And that we have high spatial resolution if you are using the Raman microscopes. So we can study these heterogeneous samples. Of course, there are some limitations, which I first already mentioned, is the fluorescence. for some samples with high fluorescence, we can try to avoid it by using near-infrared laser. That second disadvantage is it's inherent to this Raman scattering process, which is very weak. But then, of course, we can use a bit longer acquisition times. And we can also increase the power of the laser, but then we have to take into account that there could be some local heating, potentially damaging the material, or especially for black samples, because they absorb more. The instrumentation is also a bit more complex and expensive compared to some other techniques. Then, of course, not all materials will be active in Raman in Raman scattering. And then also interpretation of spectra can sometimes be complex if samples are unknown or we have some complicated mixtures. And then maybe the last one is the surface sensitivity. So since we are working with this design of the method is so that we are basically probing the surface of the samples. Okay, so let's go to the first example, practical example, which we studied in collaborations with our Turkish colleagues. And in this work, they studied crystal morphologies and formational condition of spherulites in siliceous volcanic rocks. Okay, so this is just an example of the sample, and this is an optical photograph from the microscope. So these spherulites are these spherical structures of radially arranged feldspar and quartz crystals in glassy volcanic rocks. And the motivation of the study, the idea was that the crystal morphologies provide important information about the physicochemical conditions that control the crystallization process in natural and synthetic materials. So in this case, we were doing the so-called Raman mapping. So we're using this. This is the optical photograph of the sample that was measured. So then we can in our setup we can design an area of interest, define the step, and then take a Raman spectrum in each spot to find the conditions. And then what we are presented as a result in the lab spec software of our instrument. In one window, we can see all the spectra collected from all the points on the sample. And then to analyze the sample, there are two ways we can do it to analyze this map. So in this case, we need to from preliminary measurements, we were looking for these components present in the sample: sonadine, cristobalite, and pyrite, and these are their spectra taken from the RUF database. And the first approach is to integrate the specific Raman bands related to the compound. Like, for example, for cristobalite, we can integrate the bands, the intensity of the bands of this band located at about 250. And here I have it selected in red in the software. And then for pyrite, we can choose this band, which is not overlapping with other bands at about 350. I just highlighted here. And then the last one, the sonadine, has a distinct band at about 500, which was selected. Okay, and then this is the result. Here is this map, the Raman map of band intensities of the regions that we chose. So we can see by analyzing, you can see that the cristobalite is mainly located in this area of the sample and how much. And then here are the sample is composed of sonadine. We can see the mostly green area. And finally, the pyrite has some inclusions here and there. So in the software, we can go and choose any spot. And here in this window, we can see the point spectrum of the sample in any point that we choose. Now, this window is another analysis that can be done, the result of the analysis that can be done with the software. And this is a direct fitting of the spectra, of the whole spectra to the obtained spectra. So it's done here in this window. It uses a classical least square method. So we just select the spectra, select the same colors as previously for the Raman map. And this is the result. In this window, we can see a particular fitting of the spectrum from this point. And we can see that this Raman map is kind of course, similar to the Raman map obtained by the other method. Maybe this map is a bit more reliable, but still they correlate with each other quite well. We mostly see that this is a sonodine and then some other inclusions of pyrite and then also areas of cristobalite. And here from this method of fitting, we can see also the program estimates the percentage of each component in the measured area. And then for presentation, what we can do is overlap the map of the Raman map with the photograph, and we get the final, after some smoothing of the pixels, we get the final results which were published. And here there's also two other maps which were done with when we changed the third component, and pyrite magnetite. So these are the results that we published in that study. Okay, another study. This has to do with the large-scale laser-induced graphene oxide transparent conductors. And the motivation for the study was that graphene films are the main candidates for replacing scarce and brittle metal oxide transparent conductors. But there is a challenge in the graphene deposition and patterning. And the results of this study showed that they were able to successfully deposit graphene oxide through a spray coating and then use a low-cost nanosecond fiber laser to do the reduction and thinning of this graphene oxide layer. And here in Raman spectroscopy, we characterized the sample surface as a function of laser power applied to reduce the graphene oxide to graphene. So we studied three random areas which were reduced with 50% power, 75% and 100% of laser power. And these are just the optical photographs. And then we also selected the square areas to make the Raman map. So these are the Raman maps. These were just done by integration of one band. That's why there is no colors. Basically, the brighter color or whiter color corresponds to high intensity, and the darker color corresponds to lower intensity. And the integrated band was the so-called 2D band, which is higher for reduced graphene oxide. And here we can also see there are two typical spectra or spectra from different areas marked here with these numbers 1 and 2 on each sample. And for these graphene-based materials, we have always two characteristic bands, which are called D and G band. G band is related to appears in all graphene-based materials. And the D band as well, it's usually associated with defects, related to the breathing mode of the graphene rings. And then here we can see that the main conclusions, what we draw from here is that for 75%, we saw the areas with the highest reduction of graphene oxide because this peak, 2D peak, was the highest. And we see here in the Raman maps, these white areas appear the brightest. But for the 100%, the sample which was reduced at 100% power had actually the largest coverage of reduced graphene oxide, because all the bands here, as we can see, these two example bands, the G band was always shifted from 1600 position to lower energies, which also means the high reduction of the sample of graphene oxide. And this was actually then correlated with the results of the conductivity. And then it was shown that this actually, the higher reduction also corresponds to higher conductivity with reduced thickness. That is the number of graphene layers. This work was done in collaboration with the engineering department of the University of Coimbra. Third study, which I would like to share with you, is the ongoing study of the Raman mapping of a polymethyl methacrylate, which was loaded with the electric arc furnace steel slags. So maybe if you know, the steel slag is a common byproduct of the steel making process. And upcycling of this material poses a great challenge because of its heterogeneous composition. And one promising reuse of this slag would be use them as fillers for polymers for enhanced mechanical properties. So we studied one of such sample. And here are the results of the study. Again, we see here on the left upper corner, we see all the spectra together of an area. From here, we can see about maybe 60 by 50 microns. This step was about 4 microns. So these are all the spectra. And then we were able to fit the spectra with the 3 components. So the first one is the spectrum of the polymer itself, and then 2 components that we were thinking we are sure that the sample has is larnite and magnesium-ferrite. So these are the results. So this is the Raman map of the just intensity of the regions. It doesn't work here very well because there are overlaps between the bands in the same region. And here actually the fitting mode, the fitting Raman map works a bit better. So mostly we see the green color, which corresponds to the spectrum of the polymer itself, and then the slugs, two components that we were fitting is the larnite and magnesium ferrite. They're located in these areas. So this is an ongoing study. It was just an example how we can apply this technique for such kind of studies. And then again, we have here some concentrations of this is we can mostly detect the polymer 90%, and then some percentage of concentration of the steel components of the steel slag. Another interesting study is this, which we did also in collaboration with the physics department of the University of Coimbra, and we studied self-assembled diphenylalanine peptide microtubes, which were covered by reduced graphene oxide with spiky nickel nanocomposite. So here are the advantages of such materials that this type of materials can have a high mechanical rigidity, strong strong radial piezo response was detected, enhanced conductivity, and then effective electron affinity. And then basically these potential applications in the field of energy harvesting, biosensing, and also embedded microelectronics. So let's look what we are here. So we measured Raman spectra of this material, of the complex itself, as well as only the peptide microtubes. And what we see, the peptide microtubes here, they present typical Raman bands, which are collected in this case. There is this bands related to this to the ring of the peptide. And then there are so-called amide 1 band, which is a COO band. Then we have amide 3 band related to NH and CN vibrations. And then for the complex, we have before we go to the complex, we can see that here these are the ramps of the reduced graphene oxide, which the bands we already saw before. We have the usual DG band, and then also the overtone bands here. And these 2 spectra here in the middle are the complex. So we can see the bands from the peptide microtubes and also the bands from the reduced graphene oxide. So from these measurements, there's this G band, which is a 2D band. It's another designation of the same band. This position and the shape of the band responds to single layer graphene. So this was the main conclusion that we draw from the studies. So actually, that's during deposition, this only one single layer graphene is formed. And then also by measuring this the ratio of the D band to G band, we can estimate the level of defects. And we can see that for the complex, the ratio for DG band is about 1.3, 1.5, which is more than for pure graphene oxide or for reduced graphene oxide due to the oxidation, due to the, of course, introduction of defects with nanoparticles, or interaction with this peptide microtubes template. So we also studied made a Raman map of, or rather, a map and a Raman line scan of a single microtube. And we obtained the Raman map here, and here the color corresponds to the basically shows that in this region we have the peptide microtubes. And then we also in this we made a Raman line scan along this line, and so the Raman map of peptide microtubes was obtained by integrating just the most intense peak, 1,000 centimeters, and where this band is the highest, we can see these areas with the white color. The main conclusion is that the introduction of reduced graphene has no significant effect on the molecular structure or assembly of peptide microtubes. This is important, so they do not interfere, they do not damage each other. And then also, as a result of this Raman line scan, it was done of the G band at 1587 along the peptide microtubes with a step of 1 micron. And what we draw from here is that most of the reduced graphene oxide and nickel nanoparticles compound is located at the end part of the peptide microtubes, which was consistent also with other techniques used. Okay, so one more study here is this fluorinone-based molecular crystal, which we studied again with the collaboration with the physics department. So why these materials are important is because these organic polycrystalline materials, they are lightweight, flexible, and have a low cost fabrication, and they are promising alternatives for inorganic ferroelectrics. And this one particular molecule that was studied, and it demonstrated robust high temperature piezoferroelectric properties with relatively high local piezoelectric coefficient. And this is, of course, has promises towards technological applications in electromechanical actuators, sensors, energy harvesters, and so on. And in this study, they demonstrated the thickness dependent of the piezoferroelectric properties at room temperature. So that's the tip of this organic crystal. This is how the molecules are situated in the crystal, and this is a schematic for the SPM scanning probe microscopy measurement. So we measured the Raman spectrum of this molecular crystal. This is all the bands here depicted. This is our molecule, and then we did the assignment by using also the quantum chemical calculations of each band, which band corresponds to which vibration of the molecule. So in this case, the lowest energy band here could correspond to the scissoring vibration. Then here, the next band is this due to this wagging vibration of the whole molecule. And then we have some other rocking or twisting vibrations. And then again, wagging vibration of another type. And then scissoring vibrations. And then the final vibration that's studied here was the CO, and this vibration, this is the CO stretching mode. And this mode strongly contributes to the molecular distortion along the crystallographic axis C, 001 direction, and therefore it's also observable in the in-plane IP component, in-plane component of the PFN piezo scan, which is here by blue dots, by the red dots actually depicted. So this was a correlation with the SPM scanning microscopy results. And here we also performed the Raman line scan on the same on this molecular crystal, and we integrated this the strongest band. And what we are observed, and that the intensity, so the integrated intensity of this band, was decreasing towards the end of this molecular crystal, and that means that it was also supported by other measurements. And another important deduction from these measurements was that the homogeneity of the molecular crystal, all the spectra look the same. There is no shift in the band. They are all at the same positions. They are just intensity that is dropping. And then also it was observed by the SPM method that actually the thickness is important, because the piezoelectric behavior completely changes. If for thinner samples there was a ferroelectric behavior, and for thicker samples there was a piezoelectric. So that was important to corroborate with the SPM measurements. So the last but not least is a study related to silicon, silicon nanocrystals, to nanomaterials. So it was silicon nanocrystals embedded in silica films. So many limitations of modern electronic devices could be overcome by implementing photonics into electronics. And since the silicon is the leading material in electronics, the integration of optical functions into the silicon technology would be practically very important and desirable. However, the main problem here is the efficient light emitter based on silicon, and this comes from the fact that bulk silicon is very inefficient light emitter because of its indirect band gap. So to try to overcome this limitation, we are trying to study nanostructures of silicon, and we produce silicon nanocrystals in silicon films. So they were produced by molecular beam deposition method by annealing of a silicon-rich silicon dioxide film at elevated temperatures. So here is a photograph of such a film, which was on a silicon substrate, which was etched. So here, this is a freestanding film, silicon-rich silicon oxide film. So after the heating to these conditions during a few hours, the silicon nanocrystals are formed. The typical size of the film was about up to 2 microns. This is the substrate, which corresponds here to which can be easily etched to get the freestanding films. And this is the model that we are assuming here, that we have a small silicon crystal, and the typical size with this method was about 3 to 4 nanometers. And here we have a transitional region, and then this is a silicon dioxide. And the size was corroborated also by transmission electron microscopy. We see the plates of the silicon, crystalline plates. So actually, the advantage of making freestanding films, and that we can perform laser annealing of our film, and this was done just inside the Raman microscope. So when there is no flux to the substrate of the heat, we were producing these laser annealed areas. And in this case, it was a desirable effect. So we used quite high power. So what we observed was this some sort of ring. And it was formed due to the very high temperatures in the film. So the highest temperature was in the middle. And this the size of the spot correspond more or less of the size of the laser beam. And then we studied this area in more detail. There are three specific areas that we can see here. And so this is the center. Center basically is a amorphous silicon dioxide, completely free from the silicon excess. We don't see any structures here in NTM. And then the ring area, the B, is filled with large silicon nanocrystals. Now they are of size of above, some of them are higher than 100 nanometers. And then here the area outside, of course, is the area similar, the pristine area, which has a small silicon nanocrystal. And these three areas were also studied by Raman spectroscopy. They have different Raman shifts. So in area inside the laser annealed area, we don't see any signal. The signal is very low. It just comes from this silicon dioxide. From the C area, we can see a Raman band typical for silicon nanocrystals of that size, about 3 nanometers, at about 500 500 centimeters. And then here, this 528, you can see the Raman shift of the coming from this ring region, which corresponds to this large silicon nanocrystals. And what we notice here from the spectra is that the intensity of this band is much more higher than the Raman intensity from small silicon nanocrystals. It's about 2 orders of magnitude higher. And this is due to the size effect of the resonance size effect from this large silicon nanocrystals. And the second is the shift of the Raman band by about 10 centimeters. And this shift corresponds to a compressive stress. So here, actually, we were able to estimate the stress from the theory. It was about 3 gigapascal. So these large silicon nanocrystals are formed under compressive stress. And then we took a look at a small area, more precise look at this area with the large silicon nanocrystals. What we observed here, these are our big silicon nanocrystals. And we also noticed there is a ring of holes, which here appear as a bright spots in the transmission electron microscopy. And then we focused on a specific large silicon nanocrystal here marked with this arrow. And we noticed that it has some sort of like a surface feature. The shape is not round, it's like a pear-like shape. And this shape and this part of the silicon nanocrystal was also detected in the surface in SEM, scanning electron microscopy. And it here appears as a bright spot. So this is the same area. And then the same surface feature was detected by AFM. And we also found out its height. The same area was also studied by Raman spectroscopy. So we made a Raman map of the at about 500 centimeters of the intensity of the Raman band. So we see the largest intensity in the ring region, which corresponds to these large silicon nanocrystals. Here the holes, the same position of holes is marked here. And then we have present here like three typical spectra. Spectra from point 1, which corresponds to this, which was these all the bands are very intensive compared to the outside region. And then here we notice that the Raman shift is different for all these 3 regions. So the Raman shift is at about 520 corresponds to the unstressed silicon nanocrystals. And then the further we go from the holes, or actually we found this whole crystal here or region where we have again very high compressive stress. And then we did, after some additional measurements, we just suggest that the silicon, that first of all these holes could correspond to the just silicon nanocrystals that just fell out from from the silicon film, and that's why there is less stress in these areas, closer to these areas, or that the silicon could actually erupt, because this is the same erupt from the silicon nanocrystals at this stage of formation. So that's why this crystal doesn't have any stress, because it's not symmetrical. It's not symmetrically. It's not a sphere. It has like a pear-like shape due to the silicon eruption, and it can relax stress in the vicinity. And then, of course, this that's the results of AFM, that the same crystal was studied, and we also found its height, which this part was supposedly formed by eruption of silicon, pressurized silicon at the stage of formation. Okay, so after these practical examples, perhaps now we are ready to answer the important question, is whether the Raman spectroscopy can close the loop, or rather help in studies related to circular economy. So I would say that definitely yes, because first of all, Raman spectroscopy gives us detailed information about chemical composition and the structure, which, for example, could be used to identify or characterize new materials designed for easy recycling or biodegradation. Raman spectroscopy with this Raman mapping capabilities can, for example, detect impurities in the sample that can affect performance of our material. The next important point or advantage of the technique is that this is a non-destructive analysis. The same sample can be analyzed repeatedly, if necessary, over time to track how materials degrades or change after some time or after the recycling of the uses or recycling cycles. Of course, we can also study composites and complex materials, which could be typical for production in circular economy. Then, of course, we have versatility in material analysis. We can study a very wide range of materials, like, for example, plastics, metals, composites, biomaterials. In particular, microplastic research can be easily done by the Raman spectroscopy. And also bio-based and biodegradable materials can be easily studied. These all are very active in Raman. And then, as in last examples, nanomaterials are important in circular economy and can be studied by Raman spectroscopy. And this method is effective in characterizing nanomaterials and the interactions, and also maybe developing or analyzing of nanocomposites is important, would be important for circular economy, and this can be also studied by Raman spectroscopy. And lastly, I would like to thank you for your attention.